quoted here from a more extensive explanation I got is basically the intuition that on one hand you have this graph that represents you the computation. And if you just consider, this is taken from the paper, if you just consider this expression here, which is in my gibberish handwriting, is basically logarithm, natural logarithm of x1 plus x1, x2 minus sine of x2. This is this expression. This is a function of just 2 parameters. And when it comes to deep networks, we have millions of them. So it's just 2 here. Here is this function. And you can always express this. You can represent this function as this graph, expressing each node a single operation and an edge connecting nodes as the dependencies in which the order of the different operations are performed. So that is essentially the graph the automatic differentiation is working on, and the same graph that you build when you create mathematical expression with a sequence of tensors. And so the only thing I wanted to have you think about is that given this graph, there are 2 ways in which you can actually compute the derivative. And in fact, you have automatic differentiation in 2 modes. We have the forward mode and we have the backward mode. We always talk about backward propagation, not forward propagation, for one specific reason, which I'm going to tell you in a second. And another thing I should have said is that automatic differentiation is a much more powerful framework than we actually need it into deep learning, because the kind of differentiation we're talking about is a scalar representation. So ultimately, it's going to be a number into the expression. It's not going to be another expression. So it's a very specific kind of optimization here, a very specific kind of gradient we're actually computing. But saying that, we can actually do this computation in 2 ways. So as in, we calculate the derivatives as we go, and so that's the forward, or we can calculate the derivative on the way backward. So why do we use the backward instead of the forward? And the intuition, the reason is that it's very related to the kind of problem that we're having as an optimization problem. So if we do the forward step, basically remember that you have to calculate partial derivatives to calculate the gradients. So the gradient, in case you don't know, is basically the vector in which each component is the partial derivative for that corresponding covariate parameter, call it the way you like. And if we do that in forward mode, basically we have to traverse the graph 1 time per single covariate. So in the general case, in the general setting, numerical setting that we have in deep learning, which we start with millions of parameters, millions of features, and we end up in 2 classes, 3 classes, you immediately understand that these expenses in going and calculating the covariates 1 per single feature is not paying back at all. On the other hand, in the backward propagation, and by the way, this is an implementation of the forward mode in NumPy, so you can have a go if you like. And the reverse or the forward mode is called the tangent mode. The cotangent or the backward mode is basically doing the opposite. And since it's doing from the other way around, so going in the opposite direction, it's able to calculate what is called the adjoint, because you're basically bringing you the contribution of each derivative 1 piece at a time, and you're not leaving anything back. So that's why you start from the back and you go up to the end, which is indeed the start of the network, and you finish by having accumulated all the contribution from the graph. And so that's why it's so effective. So I just wanted to share this bit because not everybody talks about it, but it's absolutely brilliant algorithm. And if you're wondering how the different frameworks, and most of them I already showed the logos in the slides, basically placed into this quadrants of having ahead of time auto differentiation of runtime, which is dynamically. And if we have model is a data structure or model is code, you can't see how they positioned. And PyTorch is in this quadrant just because you have runtime model differentiation. We understood that, and the model is code, is not data. So, and we're going to see in a second what that means. But if you're interested in these sort of things, I strongly recommend you to have a look at this paper. Okay, so what sort of facility PyTorch is bringing as a deep learning framework now? Because so far it seems like a tensor library, and a tensor library which is a very nice library as NumPy, but with steroids because it calculates the gradients for free. But what's the extra contribution it brings to the deep learning? And which makes it different from other libraries, as Tian was, for instance, or even the very same TensorFlow initiative. Basically, Torch ships with the NN package. The NN package in Torch is the essential framework of deep learning into Torch, which sits on top of the tensor backend that I already discussed with you. In the rest of these, and we're getting finally a bit of hands in the code now. This framework is basically building on some examples taken from this repository. It's a terrific repository, and you can have examples of very different levels of complications. So if you want to go like easier, or you're looking for more complicated examples, definitely check that out. It's absolutely brilliant. The first bit that NN is bringing is this sequential object. And if you're coming from TensorFlow or Keras world, you already have heard about the sequential thing. The sequential object is basically a sort of module that is tightening together, is taking together different layers of a network. In this particular case, is like using two linear layers and the ReLU nonlinearity. I'm going to give you, at the end of the notebook, a very short recap of the main difference, so all the activations typically used and all the loss functions. So apart from the sequential object, as you can see, we have support for a loss function. So PyTorch provides loss functions already. And if you basically get rid of all the comments here, you immediately realize that this is the entire algorithm I was depicting in the previous picture with which I started this notebook. This is it. So for a number of times, which usually refer to as the epoch, in this case it's going to be 500 times, I do always perform the very same operation. I do call the model with the data. So I already mentioned on the slides this morning, the model is a callable object, and the model here is a sequential bit. The model with called on the data generates the prediction. You use this prediction into a loss function that compares the generated predictions with the expected one, and the loss function in this case is mean squared error loss. So it's calculating the mean squared error loss. In particular, it's calculating the sum of the mean squared error, because that's the reduction. So the sum of the squared error, actually, and not the mean. And then the usual bit you never have to forget. The first thing is zeroing the gradient. Never forget to zero the gradient. Why, you would say? Because the gradient is always accumulated. If you zero the gradient, basically it's saying, get rid of all the contributions you got so far to the gradient, because I'm going to start a new optimization step. And then you basically trigger the backward propagation. So the zero gradient is getting rid of all the gradients accumulated in the graph in a bit, and then you start the back propagation again. The last bit in this example is that what do we do after we basically updated the backward? How the model parameters have been updated. In this example, we're doing it manually. So we are actually applying the updating of the parameters as it is into the definition of the perceptron, because this is a sort of decomposed implementation of the perceptron. What if we have a more complex layer? Do we have to do this manually? Or what if we have a different rule, so a different optimizer? And that's why the Optim package comes into play. You have different algorithms, so different optimization algorithm you can use. That rule is basically the rule of the stochastic gradient descent, but you might have different variations of that. And this is how the optimizer collects and fit into the rest of the picture. So basically you have the model which has the parameter. So the model is the entity that's keeping together the parameters that we want to learn from the data. We have a loss function here, which is what brings the update to the parameter, and the optimizer, which is basically controls these updates. So the optimizer is instantiated on the parameters of the model, and so the optimizer will be in charge of doing the update. And the update will be performed depending on the kind of algorithm, optimization algorithm we use. It ultimately will always be an algorithm based on the descent of the gradient. This is why this is how deep networks learn from data. There's no other chance at the moment. The framework is that, even if there's some work about it. But then the optimizer will be the one in charge of doing it. And so how these loop is changing. Basically now we have the optimizer, which is instantiated, as I told you. And so the first thing we do now is zeroing the gradient of the optimizer, which brings the zero propagation of the gradient to all the model. And again, backward on the loss, and then optimizer.step. Optimizer.step is what is actually updating the parameter. So it's doing an update of an update of the optimizer, so towards the minimum, gives you that idea. The ultimate question is, can we do even more than that? And the answer is yes. The answer is you can implement your own custom module. You don't need to stuck with the sequence and a sequential module, which basically gives you a very static graph again. So I'm advocating all this advantage of having the dynamic graph and this sort of things, which for sure brings you a lot of capability in debugging the code, because it's not about symbolic execution. And I'm sure if you never had the pleasure to play with that monster, basically you don't really understand what I'm talking about. But I don't definitely recommend you to do. The other bit which brings the dynamic graph so interesting, which makes the dynamic graph approach so interesting, is that you're in full control of how the graph is built. So in the forward method, which is the key method of a custom module, you decide what is the order in which the different layers are basically combined. And this order can change depending on the runtime. So it doesn't necessarily have to be always the same. You can decide some triggers, some rules on which you can change the topology of the graph. And for instance, you might want to, at some point, stop optimizing one branch of the network and keep going with another branch. This might be the case of generative out-of-sign networks, for instance. So this is how flexible this framework is. And the rest of the details is basically working with the details, really. So is like the essential learning step doesn't change. What we have changed really is the implementation of this model, which is indeed calling this custom code here. So we are in charge of what the model is actually doing. This bit, let me just skip this. This is giving you a very nice insight of how this sort of things are implemented in the backend. And so this part is interesting for you only if you're really into programming and into the Python code. So give you a reference of what the software engineering pattern for that and why you should do this instead of doing that. So for instance, implementing directly in the call method, stuff like that. So if you're not familiar or not interested at all about this sort of things, you can absolutely skip it. This is just for you to read it if you like. The only bit I wanted to mention here is that the functional APIs, so you don't really need to use a layer for activation function. They are not indeed layers, they're just functions. So where a layer is usually referred to as something having parameters requiring the gradient. The activation is not definitely in that case. So Torch also gives this wrapper, sometimes is useful, but usually you can directly call the functions there. So the last bit of the notebook is going to be quite collaborative, as in how would you implement a perceptron in Python. The collaboration was meant to be, but indeed we're running kind of out of time. So there are plenty of things I wanted to say to you, and the code is already there anyway. So you can actually work it out together, work it out on your own. And in case, let me know. Oh, there's a typo here. A line here. Sorry. And in fact, let's say that. Right. The last bit here is a very quick recap of the main activation function. I'm not going to go into details now, but if there's something I do mention which is not entirely clear to you, you might have a look at that first, and then you can ask if whatever you like. Typically, we're going to talk about sigmoid, 10H, or ReLU activation. Sometimes parameterized ReLU, so the P ReLU. And softmax is quite crucial in the classification case. But typically, we also have these loss functions. We have the cross-entropy loss, which is a combination indeed of a log softmax and of a negative log likelihood loss. So you call this to actually calculate this. You call the binary cross-entropy with logits, which basically calculate the log sigmoid and the negative log likelihood. And the mean squared error loss, reduced sum is usually the sum of the squared error. And that's it for this. The only bit, the extra notebook, I'm not going to. I actually thought not going to do is about model persistence. So how can you save your model to save the checkpoints? So I thought that could something you could do on your own in case you're interested. Let me now move on to. So now we have two options. I don't want to miss the opportunity to talk about digital pathology, which is a field on which I worked a bit on, and I have something to share with you, which is quite crucial. And the rest of it, of the time that we have left, I want to share this replication study I did yesterday, which was quite of a nice experience. So I will tell you later. Let me just give you a little bit of introduction to CNN and how they basically decline into the biomedical field. So something I should have said initially is that, as you may probably know, in the medical field you have medical images, and medical images are not RGB images, are something much more complicated for many reasons. And the complication comes at different levels. The complication comes at the level of the interpretation of what you're doing, in the kind of knowledge you need in order to be able to process them correctly. And also the complication comes at a technological level, in which you have different formats, you have a different technology playing most of the time their proprietary. There's no standard format as JPG sometimes or PNG. So the hardware is using some specific format which the software not usually likes. So it's a kind of an extra complication, apart from the fact that data is not that simple, let me say, as in an RGB in most of the cases, not always, but medical images can be very complicated. And this is the case of MRI images, MRI data, it could be CT scans, it could be ultrasound images, it could be histopathological images, and so talking about digital pathology. What I'm going to quickly introduce you is what is the machinery that enables you all of this. And this is the convolutional neural net, which has changed completely the perspective of computer vision, so standard computer vision, based on the fact that now the learning has changed. So let me just skip to the interesting bit. I want to say this first. So as I briefly mentioned, this is how a convolutional neural network looks like typically. In essence, is composed by two different components. On one hand, on the left-hand side, here you have the piece of the network which is learning data representation, and the kind of technique which is using to learn that is the convolution. So that's the technique, the strategy that is applying, and the kind of information which is learning from the data is some sort of spatial information, which is so as a representation which is invariant to the spatial transformation. That essentially is a convolutional learning. So learning the convolution. And the second bit is, so the fully connected layers, so to speak, are the very same layers you found in the multi-layer perceptron. But this time, they're not giving an input, what is usually taken from the raw data, as it was in the multi-layer perceptron. But instead, they've been working on covering the classification, in this particular case, bit, not just from the raw data, but from the synthesization of the data, from the learned representation from the previous block of the network, so the convolutional block. And this is the cut-through technology that changed completely the perspective in computer vision and also in the medical field. So this is how the convolution works. The convolution is a very simple operation, once again. So I'm trying to stress this out a lot. Essentially, the mathematics behind this is very essential. It's very simple. So if you have a look at what is the mathematical operation of a convolution, it's no more than this one. So I'm going to skip all the details in the interest of time. I'm afraid I have to skip the dropout as well, but it's fully executed and you can read it or you can replicate as you like. I wanted just to find the definition of convolution here. Well, it's this one essentially. So I usually apply this example because it's quite straightforward. So imagine that when you apply convolution, typically in the old jargon of computer vision, the convolution was synonym for a filter, image filter. So imagine that you have this filter here. So you want this filter to be activated every time you find. So sorry, you want the image that you're looking for a piece of an image which activates every time you find this shape, and this shape is what is contained in the filter. And the mathematics, the arithmetics to perform this activation, so to speak, is applying a convolution, which essentially is no more than an element-wise multiplication, pixel by pixel. When you take this filter and you move this filter on one specific region of the image, if you apply an element-wise multiplication and then a sum to come up with a number, and if you take this filter and you apply on this area of the image, you basically have a very large number, which is a clue of this area is activating this filter. On the other hand, if you take the very same filter and you move it onto this area of the image, the result of the convolution in this case will be 0, which means this area is not activating this filter. So what is the perspective that has changed with respect to the previous classical computer vision? In classical computer vision, this filter was given. So you superimposed what sort of filters you wanted to apply beforehand, before setting up the pipeline of learning. In convolution, these filters are part of the learning, and so the convolutional block in the CNN is devoted to learn these filters. So the the network is going to pass this filter initially set up with random values, because the network initially has no clue. So it sets up the values randomly, and it shares this parameter into the many channel of the image. So the very same filters have been applied automatically, and the tuning of the content of each filter is part of the tuning of the parameters of the backpropagation. So the contribution these filters get into the network is driven by the basically driven by the learning process itself. Right. So this is essentially the reason why convolutional neural networks have been so outstanding in their tasks. And let's try to have a look now at how can we use this sort of technology into an example of medical importance. Just to clarify the technical bit here, I'm going to use a database which I couldn't, unfortunately, release as it is, because it would have violated the terms of conditions. This is part of the dataset available in Kaggle. If you don't know what Kaggle is, basically Kaggle is a platform, a social platform for data scientists. But essentially, what it is nowadays is a very precious resource to engage with the community of data science, and also to get access to very high quality data set. And there's also an API here in Kaggle that you can use to automatically download the data. So you have to register to Kaggle if you want to get access to that, because you have to enable your account, and there are the instructions here. You have to enable your account and get an API key in order to do that. So it has to be automatically driven. I just got some code here that should make your life easier, and also need to install this couple of package additionally into your environment if you want to execute this code. And I put that on top. If you're running it on Colab, you should be able to do that immediately. I just played with a little bit of widgets of IPython here, should be working, just to give you some sort of interaction. So if I do put my username here and my key, which is somewhere in a file, not really S3, I have it locally, you should be able to automatically create the credential file for you. So the authenticate method should work for you. The first thing I did look for is whatever database about diabetic retinopathy was available. So diabetic retinopathy is a quite interesting problem. And some times ago, it happened that I had the opportunity to work with a pharma company. And the very first thing I did with them was a technical review of dataset methods and resources available, specifically for ophthalmology, and specifically for ophthalmology. That was the front of the eye. Diabetic retinopathy is the back of the eye. But anyway, it was about deep learning, so availability of data and models in machine/deep learning in ophthalmology. And you have no idea how big this field is, and there are plenty of resources out there. So there's really low-hanging fruit in this case. Diabetic retinopathy is a quite interesting problem, even from a medical perspective, but it's also very interesting from a data science perspective as well. It doesn't pose us any particular challenge in terms of data analysis, of image analysis, because the fundus images are usually very accessible. We don't have the problems and the issues that we usually have with other kind of images. And I'm going to give you a hint in the next couple of slides. the only takeaway message I wanted to mention here, when you look for a data set, I was basically looking for diabetic retinopathy. There are a couple of them because there are a couple of challenges actually available in Kaggle. And as you can see, users in Kaggle have made available their version of the data, which have been either pre-processed or like compressed in terms of size. So here you have the very same data set occupying 17 gigs or 157 megabytes. So this is grayscale, that's why. So you can choose whatever data set you want to play with. And this also gives me the opportunity to introduce you a little bit of additional technology here. Torch ships with a very popular package, which is Torch Vision, and Torch Vision brings you all the features, is fully fledged for anything related to computer vision in particular. It brings you pre-trained model, it brings you dataset, and also very nice operators that usually refer to as transformers. So methods and objects you can use to pre-process your data. And this is particularly the case for images. You can apply any sort of things. Ultimately, is what is usually called the data augmentation. So you want to play with rotation, different angles, and generate new versions of your data to increase the number of samples you have, and to technically substitute the training data with a new one, potentially more informative. Among the data sets it provides, there's this very useful utility class, which is image data folder, which I'm going to use it. So if I have a look at the kind of data that we have in our data, so we download the data, and basically we have images organized into 5 different folders, one per single class. And this is exactly the shape of data image data folder is expecting to. So if you bring the root directory, it's expecting you to have the labels into the name of the folder, exactly what we're looking for. So it's really straightforward. I have just to instantiate it and basically apply the transformation. The problem now here is, well, I probably want to split some training and test data. So this is when another class of usually not very popular as dataset is a subset class in Torch dataset class utility. And the subset is basically a class that takes another subset, it takes another dataset and also the list of indices, and it returns the samples related in the dataset with respect to the indices. So we can instantiate. This is how the dataset encapsulates into Torch. I didn't say that before. So what I was doing here is basically calculating how many samples do we have. So 3,662. And I'm generating that number of indices, and I'm using scikit-learn function, the usual function, to train, test, split samples in training and test in this case. Remember just to set up every time the size of the test set you were looking for and the random seed to make the split reproducible. And then I use subset. So all this encapsulation is absolutely trustworthy for me and absolutely effective because I have to write very few lines of code. So this is a hint of a very good encapsulation. The rest of it I'm going to do, and this is just technical, so nothing really interesting here, and not even from a medical standpoint. This notebook is entirely technical, and what I wanted to do is show you how can you integrate with PyTorch with the TensorBoard. TensorBoard is a product that made TensorFlow very popular back in the days and was really different. TensorBoard is essentially a dashboard that you can program and you can use to do many things, really. related to your either pre-processing or post-processing, or even analyzing, logging the information during the training. In this notebook, basically, I'm going to show you how. And TensorBoard was a TensorFlow bit. Now they opened the API. They made the API open, kind of accessible. So there is this integration with Torch, and this is absolutely effective. So what I'm going to do in this notebook, I don't have the time, I'm afraid, of going very much into the details of it, is reporting you example of how can you write data into TensorBoard. And this is the first bit. So I just take one batch of data, and I do this by iterating the data loader. I prepare a grid of images, and then I put it back into the TensorBoard. And to have a look at that, I have to execute this command. So I can probably try that. Probably I should have the previous execution I tried earlier. And so this is it. So this is running. And if I do navigate to this link here, this is how it looks like, the TensorBoard. So this specific network, this specific dashboard has been programmed one step at a time, following the execution of this code. The first thing I did was put in some images here, so you can have a look at the samples. So first takeaway message is have a look at the data that you have into TensorBoard. The second bit is have a look at the model. And the model is absolutely inspectable, and you can zoom in and out as you like. Everything is absolutely scalable. This is the convolutional network I implemented, and so this is the resulting graph. In fact, just to jump to the code now, the way the graph is created is just passing to the model a batch of data, because that's the only way in which you can actually produce this graph. And so this graph is actually recorded, and so visualized it, and to be absolutely navigable and explorable. So you can expand all the bits, and so you can technically see what are the parameters hanging here. And here you immediately point out what I mentioned previously when I said that the weights and the bias of the convolutional layers are basically shared among the different filters. Another bit I did was adding into the TensorBoard a projection, and this is the projector bit. The projection is quite interesting, and most of the cases useful, especially in the medical bit. Most of the time, you want to end up having a sort of representation in a lower dimensional case, just to understand where your data is actually putting in. So I don't really like the 3D setup. So let me just disable the 3D. I just want 2D. Oops, sorry. And then I don't want to use just PCA. I want to use some more fancy strategy, which is a UMAP, so unifold. The uniform manifold approximate projection, which is absolutely in fashion nowadays, and it's very, very powerful method for ensemble embedding, so manifold learning. The way it works is basically creating this case is a totally unsupervised representation of the data, into projecting the data into a lower dimensional embedding, so to speak. They usually refer to as embedding. Place anyway. This case is two-dimensional. Another popular one is TSNE. So the reason why you do this is just to navigate the data and see if you can see qualitatively any pattern in the data. And the last bit related to what I did here into the, so here you find the code, how you would add the embedding. The last bit I did was basically tracking the performance of the model. For the sake of performance issue I did execute this on my computer. I did just for one single epoch, so it's not entirely informative. But the takeaway message from this one is that remember that it keeps saying you should plot the precision recur curve, not just the precision and recall. And so I show you the code on how to do it. So you can't see per single class what is the average, what is the trend of having precision and recall, and how do they relate. It's important to show, in case you don't know, the precision and recall, basically because the two faces they're basically expressing two kind of related but opposite perspective on the data. So the precision is basically, if you express it in terms of information retrieval, the precision is basically the correctness, and the recall is the completeness. So you can fool either the two by just returning one single prediction which is correct, and so you have 100% of precision, but of course 0% of recall because it's just one out of plenty. And on the other hand, if you return any result as to be one single class, recall for that class would be 100% because you will have covered it, but the precision will be very low because you will have a lot of false positive or negative depending on the class you predicted. Right. So without further ado, let me just move on to another interesting bit here. I promised there plenty of things I wanted to talk about it, and I know that it was definitely too much for the time. And so before we end up to the end of it, my message to you is feel free to reach out if you like. Feel free to open issue to the material. I plan to update the material anyway to the repository. So if you either like it or don't like it, let me know, and any feedback is very much appreciated anyway. So just to give you a very short introduction of AI and digital pathology. So according to this paper, which is a paramount important paper, the use of AI into the clinical practice is going to be more and more essential. There are still nowadays quite challenges in that, mostly because there are still so open questions, and the transposition, let me say, of these techniques to the clinical practice is challenged by many problems. One of it is how can you be sure that the model, the network, the machine learning is actually learning medicine and not just a random pattern in the data. I'm afraid I won't have the time to explain that, but there are still some sort of things moving on in that direction. And there is I'm pointing you to the notebook here, which is this one, breast cancer IDC classification, in which is entirely focused on showing you some examples of interpretability on histopathological images. Sorry, the takeaway message from this one is that in the digital pathology specific field, deep learning seems to find a very nice place and seems to provide a very nice contribution. The very challenge, to be honest, comes with the pre-processing bit. So I taken this description of the problem, and this also gives me the opportunity to shout out to a very nice package the community has released, like a few hours ago, I would say. This is a very brand new package I came across, and seems to help a lot, and I wanted to share with you that. So one of the big problems you have when you have to work with this sort of image is that, so first of all, whole slide image is different from classical image because of the many things I already mentioned, because they are, first of all, very usually large in size. In fact, there is an example later on which asks you to download the very smallest image, which is 500 megabytes of a single image. So they're very large in size, and this size is basically compensated by the fact that they're very high resolution, and in addition to that, they're also multi-level, so you can have different perspective on the same data. So they're very nice piece of information to work with, but this poses a lot of challenges from the processing perspective. And for sure, given the limitation that we have on memory computation, for instance, you can't imagine to take a whole slide image, this monster big like that, with a very high resolution and lots of information embedded in it, and take this data and put it back into a deep network. There's no chance. So typically, the usual approach the community is undertaken to process this data is working on the patches. Unfortunately, I've no time to discuss the implications this patching of the image has into the experimental setting, but I would really like to, if you have questions about that, because there's an additional challenge it poses when you're going to derive per patient statistics. And so if you remember the leaking of information in the training and the test set, you have to remember what is the patient where you're taking the patches, otherwise you're basically leaking some information. You're moving the very same whole slide from training and test, just to mention one case. And so this is taken from a very nice and detailed tutorial that shows you bit by bit all the things you have to do. And honestly, these are the things that we did when we started working with it, as in taking the whole slide, pre-processing it, and the pre-process means scale the image, filter the image, tile the image, and the tiling is basically the patching. And then you score it because you want not just getting any possible tile, you just want to get the informative ones. And so you want to maybe also contouring the region of interest. And then you want to retrieve specific areas from this region of interest. So it's lots of pre-processing. And ultimately, once you have all these images, what you can do from a technical perspective. So the usual approach is basically that you start from an image like that. This is just an example, and it's just a JPG, so it's very compressed and not the true one. If you want to access the true one, there's this one, and there's the link in the notebook, and you can download it, but it's just 563 megabytes, just a single image. And so before telling you about this package here, which is absolutely nice, the usual approach the deep learning community is taking into tackling this sort of problem is to using an approach which is very popular nowadays, which is transfer learning. And transfer learning in general is the practice that you would use whenever you had to work with images and convolutional neural network. So hardly, I would say, nowadays someone would even think of starting from scratch the training of a big network as popular network. You typically want to start from trying the transfer learning first. And this is actually working, but it's absolutely brilliant as an idea because it starts from a network that has been trained on images of general type. So these images are basically trained on classical image of trucks, people, animals, and stuff like that. But they are effectively tuned into the domain of the digital pathology. To be entirely fair, there are actually paper now advocating the fact that if you use domain-specific if you use domain-specific data set to do this fine-tuning, the performance will be better. And that's not very difficult to imagine, for sure. But the entire machinery, the entire architecture of the experimental setting is based on the fact that you take this pre-trained model, you fine-tune your pre-trained model on your collection of tiles, and you can use this network either as a classification network, or better as a feature structure. So you use the convolutional bit, not entirely interested into the results of the classification. You just want the network to act as a filter execution, as an extra bit of information taken to process the data that you're actually interested into. And this is something we did. I put some reference in the notebook. The interesting bit I wanted to, so this is the full pipeline we took on when we did this feature extraction using different backends here. The hard bit at that time was basically coming up with the tiles and then the batching of the different tiles. Tiles that were basically collected by whole slide images like that, having a very high variability in terms of the kind of information, the kind of artifacts you could find into the image, and the very single processes of implementing these functions were very cumbersome, mostly because it was basically every time was a solution that has to be adapted to the single image. I basically came across this package yesterday, and this is just my shout out to that. So my suggestion to have a look at that. At the moment, this package is providing two main classes, which are essential though for the processing, and then also very highly integrated with the PyTorch transformer. I didn't have the chance to test them really yet, but I'm going to. So I will update the notebooks in the next days. If you're interested about digital pathology, I will definitely recommend you to have a look at. There are in the very few minutes we have left, there are two very things I wanted to mention. I can't talk about medical images without mentioning UNet. So at least there is a reference, and there's a reference implementation. It is by far too complicated to have it running on my computer or even in Colab sometimes. So the training is absolutely unfeasible on this sort of machinery. You need a proper server to do that. But UNet is absolutely the majesty of convolutional networks for medical image processing. It's a network specifically created for one single problem, which is not image classification, as you might do, is image segmentation, and in particular pixel-wise segmentation. This gives you an example of how would you apply pixel-wise segmentation to biomedical images. So this is a kind of a segmentation the UNet can do, as in getting rid of all the information but the interesting one, the interesting bit. And this is represented as the mask, so-called. So the mask is what you have to retain to filter from the original image. And this mask is basically learned end-to-end. And I don't have any more time left, but this structure is actually brilliant. And the key importance is basically twofold. The fact that the information is basically propagated from one branch, which is the encoder branch, to the decoding branch. So the decoding is basically supported by the other branch at the same time. So while it goes up, it still gets the gradient from the other hand. And the other bit, the other trick, is basically that the convolution is shrinking in size but increasing in filters. So that's the other trick that basically makes this network as not the one for all, but usually the solution, the model you want to try when you have a medical segmentation problem. Okay, so I almost done. The last thing I wanted to point you to at is this notebook, which I recommend you to try. And this is something I actually thought to do yesterday morning, I promise. But the outcome was absolutely brilliant in terms of scientific finding, not in essentially in the clinical outcome. The paper has it already, but from the experimental standpoint. So these authors basically released data code and papers, everything publicly, and everything absolutely reproducible. The thing is, and by the way, I got the interest to this dataset mostly because it has been published a couple of days ago into the machine learning repository, UCI. So you can download it with just a matter of a link. The only bit is that everything is coded in R, so definitely not my cup of tea. And I could do a bit of R, but I don't really like, as you might assume. And so I basically replicated all the findings they advocated in the paper using their data. I also replicated the statistics. So I verified, and there is part of this notebook in which basically I compare the numbers I do get from the statistics with the numbers reported in the paper, as this one. So the statistics are exactly the same. So everything sounds interesting. And also the very claim they do with our paper, as in selecting two single features into this data set, not entirely difficult. So you can run it on your laptop. Is actually confirmed, having executed with different code on the same data, sure, but different code for sure. This is something I implemented yesterday. So this is an example of a very good replicability of results, and also is a very quite challenging from a technical standpoint because it's a data set containing numerical features and categorical features, and that is also a challenge for deep learning to digest these categorical features because deep learning doesn't really like those. It really prefers numbers, and categories are not definitely something that it likes very much. So it is really, really recommended as an exercise for you to warm up. So it wasn't thought to be warm up, but then I wanted to the digital pathology bit. Right. So I think we're out of time. But I would say for me a few more minutes for questions if you have any.
So the participants have asked some questions in the Q&A part, but they don't have microphone access, so they can't ask them with their voices. And there's a few here that I'm not sure if you've seen.
Not really. No.
But okay, so can you see them over the right-hand side of the screen where it says participant engaged?
Yes, I'm looking at it. Right.
Okay, cool. And I also just wanted to thank you again, Valerio. There's like so much material there. I feel like I have some like new papers to read there. And also, I just wanted to remind the participants that we will be sending out a kind of feedback form for all of Data Week. So about this session, but all the other sessions as well. I think it's going out this afternoon. So if you could keep your eyes peeled for that, it'd be really useful to us if you could fill that out.
Yeah, there's just a very so you answered the question already about the COVID-19. The only contribution I wanted to make in that regard is that I came across a couple of papers that I hadn't as you know, there are plenty of things I wanted to say. I hadn't the chance to mention, but I can definitely point you to that because it's very educational in terms of how you set up an experimental setting which is robust in the first place. And so, as in, you can really believe in what you're getting from the data. I think I have to switch browser. I have it in the other browser. So it's posted to the one of the most popular, there you go, data set currently available, and the reference is this one. So the reference for the GitHub user is IEEE 8023, and the COVID chest X-ray dataset. So here are the papers referenced here, which says in a very red note bullet point, do not claim any diagnostic performance here because of that two papers. And I recommend everyone here to have a look at that. They're very simple studies, but very essential in their finding, as in ultimately the question is always that. So is the model really learning something which is really medical, or is it just like focusing on something? And what we got as in a potential good result is just because the quality of the data is worse, or because the number of samples that we got is so imbalanced that the model is basically focusing on the majority of class. And so in one of the papers, they're actually taking the CT scan, because CT was one of the things that everybody into this started doing to tackle this ghastly virus. And so they taken this data and they basically occluded everything into the image with a very big square, black square on the image, and they tried to train the very same model on that, and they realized basically the model was looking at something else to derive the conclusion about the COVID. So it was not looking at the CT at all. So absolutely interesting in terms of how to properly set up an experimental pipeline. So there's a question asking what ideal deep learning for longitudinal multidimensional data. That's a very good question, and so in longitudinal setting, typically you have the information over time, which is very important, and you want that to account for your learning process. So typically, I would go for some recurrent neural networks. So those kind of networks that are like having feed connections. They're not just feed forward. They have loops in it, and they're very good advances because usually the learning of the embedding into the what represents the memory, let me say, they usually refer to that. Of the network was the hardest part to train, and now it comes to the attention mechanism, which is essentially a strategy to learn better this internal representation, and this is very effective in fields like signal processing or speech recognition or language translation, so machine to machine translation or machine translation in general. There's also a paper released a couple of days ago, not days, but 1 week for sure, which was absolutely nice and definitely something I wanted to have when I was doing my PhD in software engineering. Is a deep learning model which basically translates one language to another language automatically. So as in you have Java, it gets Python, and the other way around. So these sorts of things are actually benefiting for the temporal information. So that is the first thing I would try. But then, having multidimensional data, I would also suggest you to combine the recurrent network with convolutional data, convolutional network. This is something I worked with a colleague about weather forecasting, it was related to precipitation forecasting, nowcasting specifically, so as in forecasting a very short time period. And the kind of network we used was a combination of recurrent network plus convolution, so in the same model, so that you can learn either temporal information and spatial information in the same model. Another question is, so the only way to check is just not picking up erroneous pattern is to cross-check on other types of data. That's a good question. There is a boundary to that, though, which is something all the machine learners and researchers are actually never talk about, which is the underlying assumption that you're making when you're working with machine learning. So you're assuming that the model is going to be able to generalize if the data on which you test the model on is taken from the same distribution. If the distribution is different, there's no way in which the model is going to learn unless you fine-tune the model. So that is one bit, and this is the big difference from causal models that don't look for correlation, they really look for causation. And there's a big chapter open now in the community towards what is called causal machine learning. So at some point they probably will find a meeting point on one hand. On the other hand, the rule of thumb, my suggestion would be apply for robust metrics and apply for robust experimental setting. If you have a look at the notebook, you will see that doing just one train test split is never enough. And if you do hundreds or different of the very same data set and not that big data set, you will see how the model changes in terms of predictive performance. And this will make you having a sort of rule of thumb strategy to understand if the model is underfitting, is overfitting, how that is doing, stuff like that. So that would be my suggestion. Oh, thank you, Nat. You shared the link. Thank you very much. Yeah, I think I replied to that as well. Is there an end-to-end solution for unsupervised learning as well? Yes. So autoencoders or UNet is one of that kind. It's somewhat unsupervised.
Cool. That seems like maybe all the questions then that you've answered. Yeah, thanks again, Valerio. That was great. Yeah, I learned a lot. So I hope everybody enjoyed themselves. And then just one more time, if you do see the email about the feedback form, it would be really helpful to us if you could take the time to fill that in. Okay, thank you.
Fab. Thank you so much for having me, for being so patient for this extra 10 minutes. Have a good day.